Welcome back. We have been discussing contributions to equilibrium constant. We have taken certain examples for discussing insights into different contributions that can go into explaining the equilibrium constant in terms of population of the various energy levels corresponding to reactants and products. In the previous lecture, we were discussing a special case where the reactants have only one ground state available and the product P has energy states which are like uniform ladder of energy levels. And then by using an expression for equilibrium constant which is equal to the ratio of the molecular partition functions corresponding to products and reactants into exponential minus delta E naught by RT. And then we discussed that since it has only one energy level, so Q is 1, and here we used the partition function for a uniform ladder of energy levels, and after substitution we got this result. And that result is that equilibrium constant is equal to Boltzmann constant into temperature divided by this energy separation into exponential minus delta E naught by RT. Note that this delta E naught is a positive number here. And then we started discussing Le Chatelier principle. Recognize that this particular example is of an endothermic reaction because the energy corresponding to product is higher than the energy, 0 point energy corresponding to the reactants. Now let us discuss effect of temperature. Effect of delta E0 and temperature, both we will discuss. First of all, case number 1, if delta E0 is positive and large, what I am trying to say here is that if this difference is very large, then this exponential term, if delta E naught is very large, that means what will happen? If delta E naught is very large, then the value of equilibrium constant is going to be small. So if delta E naught is large, that means exponential minus large quantity, which is equal to 1 over exponential large quantity, that is going to reduce the value of K. So K is going to be small. If K is small, what that means that the population of the various energy levels corresponding to product is also small. It makes a sense because if delta E naught is large, most of the molecules will be in the energy state corresponding to R. That means K is going to be small. The second example or second case we will choose if delta E naught is small but positive. Now you assume that this delta E naught is not very large. It is positive but not very large. Then this is a reasonable number. Remember, if we were saying if delta E naught is large, then this factor is going to dominate. If delta E naught is small but still positive, this is a reasonable number, but this pre-exponential factor is going to dominate. That means if we increase the temperature, then more and more molecules will occupy the energy levels corresponding to the product. So that means the equilibrium constant is also going to increase. I repeat, if delta E naught is small but still positive, in that case, this is a reasonable number and the overall value of K is going to be dependent upon this temperature. So according to this, if you increase the temperature, Kt by E term is going to increase. So therefore, the equilibrium constant will increase. Isn't it in accordance with the Le-Chatelier principle, which says that for an endothermic reaction, if the temperature is increased, the value of equilibrium constant is going to increase. Therefore, based upon these considerations, we took only one energy level for reactant and we took a uniform ladder of energy levels for product. We derived some equation and based on that equation, we have been able to explain the effect of temperature. Our explanation is consistent with Le-Chatelier principle. Remember that delta G naught is equal to minus RT log K. This particular discussion suggests that we cannot explain everything just based upon delta G naught. It is not just delta G naught, but its components. Delta G naught has two components. One is delta H naught and the other is T delta S naught. I would say minus T delta S naught. So these two components are explained by this differences in 0 point energy levels. This particular example belongs to endothermic reaction. So therefore, for the reaction to be spontaneous, for an endothermic reaction, there has to be sufficient increase in entropy, and that factor will be taken care of if more and more molecules here occupy these densely populated states of the product. That will explain the increase in entropy for the process. So it is not just the free energy, its components delta H naught and minus T delta S naught become very, very important in providing mechanistic insights into the process under consideration. So these were the various contributions to equilibrium constant. It is very important to address these contributions because delta H naught, delta H, in other words, the enthalpy depends upon the nature of interaction. And entropy change depends upon not only the interaction, but also associated with the changes in the surroundings. So it is not only the association between the two reactants. If that association between two reactants lead to release of lot of solvent molecules which were earlier oriented around the reacting groups, and that release can increase the entropy. And here in terms of statistical thermodynamics, we are explaining that in terms of the population of various energy states. So not only enthalpy, but entropy change is also very important consideration. By now, we have discussed all thermodynamic quantities, starting with internal energy, we discussed entropy, we discussed Helmholtz energy, Gibbs energy, enthalpy, heat capacity, mean energy, and then we have now discussed the equilibrium constant. We have connected all these thermodynamic quantities with either canonical partition function or molecular partition function. So in a sense, now we have shown that all these thermodynamic quantities can be experimentally measured with the help of spectroscopy. All right. Now, a couple of lectures we will spend on solving numerical problems. One such numerical problem, let us take it up today. The question is, calculate the vibrational contribution to molar heat capacity of nitrogen gas at 1000 Kelvin. The experimental value is 3.43 joules per Kelvin per mole. The question is calculation of vibrational contribution to molar heat capacity. How do we begin answering this question? First of all, we need to first decide that how to connect this molar heat capacity with something which may depend upon the molecular partition function. Molar heat capacity or heat capacity is change in internal energy when 1 degree centigrade temperature change occurs in a system at constant volume. So what we have now is to calculate the vibrational contribution to molar heat capacity of nitrogen gas at 1000 Kelvin. The experimental value is given to us. And we know that heat capacity CV is equal to del U by del T at constant volume. This we know. We also know that CVM is equal to Avogadro constant into temperature derivative of mean energy at constant volume. That also we know. So that means, why don't we first get an expression for the mean energy? Mean energy is minus 1 by Q into del Q by del beta at constant volume. Let us do that. We know that we are going to now derive an expression for mean vibrational energy, which will be minus 1 by Q vibrational into del Q vibrational del beta at constant volume. This is what we are going to do. We also know that Q vibrational is equal to 1 over 1 minus exponential minus beta E. Therefore, your mean vibrational energy is going to be minus 1 by Q. That means minus 1 minus exponential minus beta E. This is minus 1 by Q into derivative of 1 by exponential minus beta E. This is going to be minus 1 over 1 minus exponential minus beta E square into minus exponential minus beta E into minus E. This is all going to be the expression for EV, that is minus 1 by Q, this is minus 1 by Q, into derivative of this is minus 1 by 1 over 1 minus exponential minus beta E square, and derivative of this, which is minus exponential minus beta e, then derivative of minus beta e is minus e. All right. So, what it comes to now? This is cancelling with this, and we have e exponential minus beta e over 1 minus exponential minus beta e. I can write this again as e over exponential beta e minus 1, which is equal to hc nu bar over exponential hc nu bar by kt minus 1. But remember, hc nu bar is equal to k times theta v. So I can write this k times theta v divided by exponential hc nu bar by k is equal to theta v. So theta v by t minus 1, right? So therefore, my mean vibrational energy is k times theta v over exponential theta v by t minus 1. So what I have now? Mean vibrational energy is k times theta v over exponential theta v by t minus 1. This is what I have. Let us double check. K times theta v or exponential theta v by t minus 1. Now we are interested in CVM, which is equal to Na times derivative of delta E by with respect to T at constant volume. And since there is no volume term appearing in this, I will as well may not write at constant volume, but it's okay. So this is Na times, I need to take derivative of this, which is k theta v, these are constant numbers, into minus 1 over exponential theta v by t minus 1 square into derivative of theta v by t, this will be minus theta v by t square. What I have now? I have k times Na into, there are two theta v's, theta v square by t square, minus minus cancel, into 1 over exponential theta v by t minus 1 square. K times Na, this is R. Now you see I have this derived this equation. CVM is equal to R times theta v by t whole square into, yes, there has to be another term over here. There has to be exponential theta v by t, yes, exponential theta v by t, yes, we put there. So exponential theta v by t over exponential theta v by t minus 1 whole square. That means now if I have the numbers for theta v and temperature, I can easily get the value. Theta v can be calculated from hc nu bar is equal to k theta v. From the knowledge of Planck's constant, speed of light, wave number is already given 2344 centimeter inverse, k Boltzmann constant, you can get theta v. That means your theta v is going to be hc nu bar by k. Substitute the numbers and you get a value of theta v, which is 3374.k. 3374 Kelvin. Now theta v by t, t is 1000. So theta v by t is 3374 by 1000, which is 3.374. You have the value of theta v, you have the value of theta v by t, substitute. What you get is constant volume molar heat capacity equal to 3.48 joules per Kelvin per mole. Continuing this further, it also says calculate the fraction of molecule in Vth vibrational state. Fraction, population, Pi is equal to Ni upon N is equal to exponential minus beta Ei upon Q, that we know. Therefore, if I replace Pi by fraction in the Vth vibrational state, this will be equal to exponential minus beta vibrational energy level divided by Q vibrational. And what are these vibrational energy levels? V Hc nu bar, because we know it is V plus half Hc nu bar. Half Hc nu bar we ignore. Remember the discussion in the vibrational partition function. And we also know that Qv is equal to 1 over 1 minus exponential minus beta Hc nu bar. Once you have that, substitute this, you end up with this expression. Once you have this expression, then it is a matter of just putting the numbers. The fraction is given by this. To calculate F0, use V is equal to 0. To calculate F1, use V is equal to 1. That's all. You are already given the wave number. V value can be variable. Beta is 1 over kT. H is Planck's constant. So use those numbers, substitute over here. You will find out that the fractional population of the ground state is nearly 1. And the first excited state, the fractional population is 1.31 into 10 raised to the power minus 5. It is so less. This comparison suggests that even at the temperature which is given, temperature given to us is 1000 Kelvin. Even there, you see the fractional population in the first excited state is only 1.31 into 10 raised to the power minus 5. That means most of the molecules are in the ground state only. So therefore, with the knowledge of the partition functions corresponding to particular mode of motion and the fractional population, we can calculate the fractions of the molecules in the ground state, fraction of the molecule in the first excited state, provided we know, we remember the formulae, or we are able to derive the formulae appropriately. In the lectures ahead, we are going to take up more examples and do some calculations so that the applications of the derived equations become easier to understand. Thank you very much.